Morning. I'm going to read this lecture in first person, so for the next 40 minutes or so, you can imagine that I am Ray Davis with a little bit more hair. I'd like to start out by introducing you to neutrinos. They are neutral, nearly massless particles that move at nearly the speed of light and easily pass through matter. A neutrino passing through the Earth has only one chance in 1,000 billion of being captured. Wolfgang Pauli postulated the existence of the neutrino in 1930 as a way of carrying away missing energy, momentum, and spin in beta decay. The sun derives its energy from fusion reactions in which hydrogen is transformed into helium. Every time 4 hydrogens are turned into a helium atom, 2 neutrinos are produced. These neutrinos take only 2 seconds to reach the surface of the sun and another 8 minutes or so to reach the Earth. Thus, neutrinos tell us what happened in the center of the sun 8 minutes ago. The sun produces a lot of neutrinos. Even at the Earth, 150 million kilometers from the sun, about 100 billion pass through your fingernail every second. They pass through the Earth as if it weren't there, and the atoms in your body capture a neutrino about once in a lifetime. As we will see, neutrinos captured me early in my career. I received my PhD from Yale in 1942 in physical chemistry and went directly into the Army as a reserve officer. After the war, I decided to search for a position in research with the view of applying chemistry to studies in nuclear physics. After 2 years with the Monsanto Chemical Company in applied radiochemistry of interest to the Atomic Energy Commission, I was very fortunate in being able to join the newly created Brookhaven National Laboratory. Brookhaven was created to provide peaceful uses for the atom in all fields of basic science, chemistry, physics, biology, medicine, and engineering. When I joined the chemistry department at Brookhaven, I asked the chairman what he wanted me to do. To my surprise and delight, he told me to go to the library and find something interesting to work on. I found a stimulating review by H.R. Crane. You can see here that neutrino physics was a field that was wide open to exploration. It wasn't even clear that they existed. Neutrinos also turned out to be very suitable for applying my background in physical chemistry. So how lucky was I to land at Brookhaven, where I was encouraged to do exactly what I wanted and get paid for it. Crane had quite an extensive discussion on the use of recoil experiments to study neutrinos. As you can see from my first entry on the first page of my first Brookhaven lab notebook, I immediately became interested in such experiments. I spent the first year working on the recoil of silver 107 from the electron capture decay of cadmium 107, but these experiments were inconclusive. My first successful experiment was a study of the recoil energy of a lithium-7 nucleus resulting from the electron capture decay of beryllium-7. In a beryllium-7 decay, a single monoenergetic neutrino is emitted with an energy of 0.862 MeV, and the resulting lithium-7 nucleus should recoil with a characteristic energy of 57 electron volts. A measurement of this process provides evidence for the existence of the neutrino. In my experiment, the energy spectrum of a recoiling lithium-7 atom ion from a surface deposit of beryllium-7 was measured and found to agree with that expected from the emission of a single neutrino. This was a very nice result, but I was scooped by a group from the University of Illinois. During this time, I began working on a radiochemical experiment for detecting neutrinos using a method that was suggested by Bruno Pontecorvo in 1946. Pontecorvo's short paper was quite detailed and described removing argon by boiling carbon tetrachloride and counting argon-37 in a gas-filled counter. This paper was a report from the Chalk River Laboratory in Canada and was classified by the Atomic Energy Commission because it was feared that the method could be used to measure remotely the power output of reactors. Luis Alvarez proposed in 1948 to use the chlorine-argon reaction for detecting solar neutrinos using a large tank of sodium chloride solution, but did not choose to pursue the experiment. Since no one else appeared interested in attempting the chlorine-argon neutrino detection method, it seemed a natural and timely experiment for me to work on. The Pontecorvo method makes use of a reaction in which a chlorine-37 atom captures a neutrino to make argon-37 and an electron. This reaction here. Argon-37 is a radioactive isotope that decays back to chlorine-37 by the inverse of the capture process, with a half-life of 35 days. The threshold for this reaction is 0.814 MeV, meaning that neutrinos with energies of less than this energy will not be captured. There are two potential sources of neutrinos, if you just want to sort of look for them, fission reactors and the sun, both of which were suggested as possible sources by Pontecorvo. At this point, I'd like to tell you a little bit more about the sun and how it produces neutrinos. As I said earlier, the sun's energy comes from the fusion of 4 hydrogen atoms to make a helium atom. I'd now like to explore these reactions in a little bit more detail and note which ones can produce neutrinos that could be detected with the chlorine-argon experiment. The relative rates of nuclear reactions in the sun are based on detailed modeling of temperatures, pressures, and elemental abundances in the sun, into which are put laboratory-measured rates of appropriate nuclear reactions. What I'm showing here represent current best estimates. These estimates have changed with time, but have been pretty stable since the late 1960s. Most of the time, 2 hydrogen atoms, protons here, react to make a deuterium, a positron, and an electron neutrino. But the energy that's released in this electron neutrino are quite low and cannot be detected with the chlorine experiment. One time out of 400, 2 protons react with an electron to make a neutrino, a deuterium and a neutrino with a little bit more energy. These are quite energetic, but there aren't very many of these kind of neutrinos. So the next thing that happens, all of the deuteriums react with a proton to make a helium-3 and a gamma ray. And then most of the helium-3s react together to make helium-4 and release 2 protons. This is 85% of the time. And the other 15% of the time, a helium-3 and a helium-4 react together to make a beryllium-7 and a gamma ray. Nearly all of the beryllium-7 then captures an electron to make lithium-7 and a neutrino. And the lithium-7 then captures a proton to make 2 helium-4s. Remember that helium-4 is the ultimate product. But you can see there's a branch here. Most of it captures an electron. But 1 in 10,000 beryllium-7s captures a proton to make boron-8 and a gamma ray. And this boron-8 then decays to 2 helium-4s, an electron, and a neutrino. And this neutrino has a lot of energy. And these are the neutrinos from this reaction produce most of the signal that I eventually measured in my experiment. Everything is summarized on this slide. So 2 protons make a deuterium. That makes a then make a helium-3. Most of it goes to helium-4 here, but there's a significant branch to beryllium-7. And then beryllium-7, there's a minor branch here, but it produces these energetic neutrinos. It's only this last branch that's really important has neutrinos energetic enough to drive the Pontecorvo reaction. Here you can see the fluxes of neutrinos per square centimeter per second at the Earth, calculated in the most recent calculation by Bahcall and Pinsonneau. The chlorine experiment is sensitive to the boron-8 neutrinos, which is this curve here. There is also some contribution to the chlorine experiment, this shaded area here, from so-called PEP neutrinos and from the beryllium-7. There's one more thing to do before I return to history. Here's the definition of the units we use to measure solar neutrino flux, the SNU, or solar neutrino unit, which is 1 capture, 10 to the minus 36 captures per target atom per second. And I also want to tell you the final answer from my experiment so you can compare it with earlier measurements, and that is that the measurement I found was 2.56 SNU. In my first experiment using the Pontecorvo chlorine reaction, I tried to detect neutrinos from a fission reactor using carbon tetrachloride as a target material. I exposed a 1,000-gallon tank of carbon tet at the Brookhaven Graphite Research Reactor for a month or so, removed the argon, and counted it in a small Geiger counter. That reactor did not have a high enough neutrino flux to detect with this target size, so neutrinos were not observed. Furthermore, a reactor emits antineutrinos, and the Pontecorvo reaction requires neutrinos. It was not clear, however, at that time whether neutrinos and antineutrinos were different particles, nor was it clear how they could differ. After all, there are other examples in nature where a particle is its own antiparticle, for example, the photon and the pi-0. The background due to cosmic rays was significant, so as part of the experiment, I buried a 1,000-gallon tank of carbon tet 19 feet underground. From the background corrected argon-37 count rate, I was able to obtain an upper limit on the solar neutrino flux. As you can see, the limit was 40,000 SNU, a factor of 15,000 above my eventual result. One reviewer, as you can see, was not too impressed with this, with my upper limit. As he said, that would be like standing on a mountain, reaching for the moon, and concluding the moon was more than 8 feet from the top of the mountain. It was clear that the Brookhaven reactor was not a powerful enough neutrino source. So in 1954, I built an experiment using 1,000 gallons of carbon tetrachloride in the basement of one of the Savannah River reactors, the most intense antineutrino source in the world. One can calculate the total capture rate from all fission product antineutrinos by chlorine-37, presuming neutrinos and antineutrinos are equivalent particles. The sensitivity for detecting neutrinos and the flux at Savannah River were sufficiently high to provide a critical test for the neutrino-antineutrino identity. I did not detect any reactor neutrinos and found that the neutrino capture rate was a factor of 5 below the antineutrino capture rate. I later did a 3,000-gallon experiment at Savannah River, which lowered the upper limit for neutrino capture to a factor of 20 below the antineutrino capture rate. While I was at Savannah River, Fred Reines, Clyde Cowan, and their associates were performing a beautiful experiment, the first detection of the free antineutrino. The Reines and Cowan experiment was a clear demonstration that neutrinos postulated by Pauli was indeed a real particle. And now we return to solar neutrinos, this time for good. In the 1950s, it was thought that the PP1 reaction of fusion reactions, in which two neutrinos produce a deuterium, a positron, and a neutrino, was the only significant source of neutrinos, but their energy was too low to detect with the chlorine-37. So here is the same thing I showed you before. The PEP reaction was not known, and this reaction was not thought to be important. It was only less than a 1 in 10,000. That's why I show it in pale colors here. There was another possibility, and that is a CNO cycle, in which there's a cycle of nuclear reactions that allow 4 protons here, 1 proton here, 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 and here, and then producing a helium-4. So the carbon-nitrogen oxygen act as a catalyst in some ways, allowing 4 protons to make a helium-4. And this releases 2 fairly energetic neutrinos. It was not clear at the time, this is in the late 1950s, whether this operated in the sun or not. The situation of which nuclear reaction is important changed dramatically in 1958, with Holmgren and Jonson's report that the reaction of helium-3 with helium-4 was 1,000 times greater than previously expected. It was immediately recognized that the path, now about 15% of the time rather than 1 in 10,000, through beryllium-7 was significant. Furthermore, the beryllium-7 could react with a proton, become boron-8. These 2 radioactive products, beryllium-7 and boron-8, would be the source of energetic neutrinos. The relative rates of electron and proton captures on beryllium-7 were not measured, but estimated rates allowed the possibility that virtually all of it captured a proton to make boron-8. The decay of boron-8 to beryllium-7 would be accompanied by neutrinos with the typical energies of 7 MeV. Willie Fowler and Al Cameron immediately relayed to me these developments. They pointed out that the neutrino flux from these sources could perhaps be easily observed with the chlorine-argon detector. The initial estimate was quite optimistic, several captures per day in 1,000 gallons of carbon tetrachloride, or perchloroethylene. So at this time, we set up a 1,000 gallon in the Barberton limestone mine near Akron, Ohio. Here you can see me and my technician, John Galvin, extracting argon from our 2 500-gallon tanks of perchloroethylene. Our initial results were disappointing. We didn't detect any clear signal of neutrino-produced argon-37. This is just an upper limit of 3 plus or minus 5 counts. I first began collaborating with John Bahcall in 1961, when Bahcall calculated the beryllium-7 electron capture rate after I pointed out the importance of knowing this reaction rate. At about this time, Ralph Cavanaugh measured the beryllium-7 p-gamma reaction rate, which is the one that produces boron-8, and found it to be disappointingly low. It is the ratio of the two reactions to consume beryllium-7 that is so discouraging. With most of the beryllium-7 capturing an electron to make lithium-7 rather than a proton to make boron-8, it would be very hard to detect neutrinos from the sun. As you can see from this quote from Fred Reines, I was not the only one who was discouraged. Even hundreds of thousands of gallons, you might not detect anything. The situation brightened considerably in 1963 when, you can see the reason for our discouragement here. Unlike the 1958 prediction of up to 100% of the beryllium-7 capturing a proton, in the early 60s, when the electron and proton capture rates were better known, the proton capture only occurs 1 out of 10,000 times, so most of the branch goes up here. The situation brightened considerably in 1963 when John Bahcall carefully calculated the capture rate of boron-8 neutrinos and showed that the rate was 20 times higher than previously expected. This is the capture rate in chlorine-37. This led us to propose a large chlorine experiment. The theory and experimental approach were laid out in back-to-back papers in 1964. The theory provided guidance as to how large a tank to build, and our measurements at Barberton told us how deeply it needed to be buried. This marks the beginning of my long collaboration with John Bahcall. Bahcall has been the keeper of the standard solar model for nearly 40 years and has been and continues to be a major force in promoting measurements of appropriate nuclear reactions, promoting solar neutrino experiments, and making other tests of the solar model. It is clear without the point of reference the standard solar model provides, there would be no solar neutrino problem. The Barberton experiment was unsuccessful in detecting solar neutrinos, but very useful in predicting the cosmic ray muon background for the larger experiment. These events of the late 1950s and early 1960s ultimately led Brookhaven Lab, with the support of the Chemistry Office of the Atomic Energy Commission, to build a 100,000-gallon chlorine-argon neutrino detector in the Homestake gold mine in Lead, South Dakota. The scale of the experiment was determined by a theoretical estimate of the expected neutrino flux and the neutrino capture cross-sections for each solar neutrino source in the sun. I'd like to now go through the construction of the experiment and explain how it works. The construction of the experiment was detailed in a series of articles in Sharp Bits, which was published by the Homestake Mining Company for its employees. Here we can see miners drilling holes for rock bolts in one of the short tunnels leading into the experiment. The excavation for the main chamber is about half finished here. This large beam on the ceiling is for a crane for moving heavy objects within the room. Here now the large chamber is ready for the tank. The surface of the chamber is covered with rock bolts and chain link fence to keep the roof from collapsing. The tank itself was built by the Chicago Bridge and Iron Company, which was known for building municipal water tanks of this sort, reactor containment vessels, and space simulation chambers, and other large tanks. So they had a lot of experience in this. The tank was built in pieces of the largest size that could fit into the mine hoist. You can see one about being put in here. Some of these pieces are a pretty tight fit into the mine hoist. Here now the pieces of one end of the tank are laid out on the floor of the large chamber like flower petals. A large motor-driven roller was used to rotate the tank while it was being welded together. Here the roller is being moved in by a small train into the main chamber. Here now the tank is about half finished. All of the welds in the tank were checked by X-ray. Here some workers are mounting an X-ray source right along the axis of the experiment. Then they attached X-ray film all the way around the outside of the tank and exposed it to X-rays from that source I showed previously. Here now is the tank completed but not painted yet. The next step was to vacuum leak test the tank. The entire tank was pumped out by this 12-inch diameter diffusion pump and then leak tested using a helium leak detector. In order to extract argon from the tank, helium is bubbled through the perchloroethylene. This was done very efficiently using a device called an eductor. And here it's being shown in the Brookhaven Lab swimming pool. I should point out that the swimming pool here is filled with water, not perchloroethylene. This is what the eductors look like inside the tank. This drawing shows the layout of the experiment. Here's the tank, obviously. Two pumps here are used to circulate perchloroethylene through the eductors. And then the helium is circulated through the top of the tank and then through the control room. The flow rate of perchloroethylene was about 1,500 liters per minute. During an extraction, the helium atmosphere in the top 5% of the tank was circulated at 17,000 liters per minute through the control room. A large condenser here near the tank freezes out perchloroethylene, and a charcoal trap in the control room, held at liquid nitrogen temperature, traps the argon. About 95% of the argon in the tank is removed in 20 hours of circulation. Here are the two pumps. This is me coming through the door, and this is Gerhard Friedlander, who was the chairman of the chemistry department at the time. He's seen adjusting one of the pumps. The control panel for the circulation system is inside the control room. Here I am with John Galvin, who was a technician with me for many years. Notice that 35 years ago, we didn't kick people outside to smoke. The charcoal trap, shown here hanging under the table, is held at liquid nitrogen temperature. Because of the large volume of helium circulated through the system, a lot of liquid nitrogen was used. After the argon is trapped, it is purified and placed in tiny proportional counters. You can see how tiny the counter is in my hand. The counters have an internal volume of 0.25 or 0.5 cubic centimeters. In the early years, samples were counted at Brookhaven Lab, inside shields made from battleship gun barrels built before the atomic bomb. They were cut into sections. This is probably the best known picture of the tank, freshly painted and ready to go. In order to forecast as accurately as possible the rate of solar neutrino capture in the Homestake detector, it was necessary to measure the production cross-sections for some of the neutrino-producing reactions and derive their rates in the interior of the sun. This great effort was largely carried out at the California Institute of Technology under the leadership of Professor William A. Fowler. Many nuclear astrophysicists and astronomers contributed to the basic physics that supported this early effort in solar neutrino astronomy. Our task at Brookhaven was far simpler, and we, Don Harmer, Ken Hoffman, and myself, had the fun of building a large detector and making it work. The Homestake experiment became operational in 1967. Even after the first couple of runs, it was clear that the solar neutrino flux was lower than that predicted. This is the first correspondence concerning new data, a letter to Willie Fowler. Already the measured rate was 1/3 that predicted by Bahcall and Shaviv. You can see I was already alarmed at the low rate. I will collect another sample in September. We are ready now. Turn on the sun. We reported our first results in September 1967, when we reported an upper limit corresponding to 3 SNU, about a factor 3 below the rate predicted from the standard solar model. As you can see, collection of nearly 30 years of data and 30 years of refinement of the standard solar model have greatly improved precision, but the numbers haven't changed much. The sun produces about 1/3 as many energetic boron-8 neutrinos as expected. So you can see here, the prediction is 7.5 30 years ago. It's 7.6 today. My upper limit was 3. The final number is 2.56. Here's the data from our first paper reporting results, published in May 1968 in the Physical Review. The title of the paper was Search for Neutrinos from the Sun. As everyone knows, when you put search for in the title of your paper, it means you didn't find any. As you can see, the argon from the tank and the background are about the same. You can't really see. This is from the tank, this is the background. You really can't tell the difference. It was clear that we had to reduce the background. Brookhaven electronic engineers Velko Radica and Lee Rogers solved this problem by devising a pulse rise time system to discriminate argon-37 decay events from background events. Let me explain how this works. Here's a proportional counter. When a decay occurs, ion-electron pairs are made inside the gas volume, and the electrons move rapidly to the center wire, making an electrical pulse. The size of this pulse depends on the number of electrons produced, which in turn depends on the energy of the decay. The dominant decay mode of argon-37, k-orbital electron capture, deposits 2.82 keV of energy into the counting gas in the form of Auger electrons from atomic electron rearrangement. These Auger electrons have a range of about 100 micrometers, and about 100 electron ion pairs are generated. All the ions, so they're generated in a very short track, and all of the ions have about the electrons have the same drift time to the center wire, resulting in a rapidly rising pulse. The principal background is from gamma ray interactions with atoms in the counter, which generate Compton electrons. These have a much larger range, making a track all the way through, which generates a more slowly rising pulse. Here's a plot of data collected with the new system. In the appropriate energy window, which is about in here, there are a number of counts. The rise time is expressed in this ADP signal, and counts with the appropriate rise time are shown in this pink window. Only the green points are genuine argon-37 decays, and the other ones here are background. We began using this new system in 1970. After about 1 year of observations, a clear neutrino signal was observed. We did some other things to lower backgrounds. We moved the counting apparatus to the mine, taking advantage of the mile of rock to reduce cosmic ray backgrounds in the counters. We filled the room with water, which eliminated a minor background and provided perhaps the world's deepest swimming hole. The pulse rise time development gave the Homestake experiment a new life. The solar neutrino production rate was indeed lower than the solar model predictions by a factor of 3. The most likely explanation, in my view at the time, was that the solar model was in error. Many physicists believed there was something wrong with our experiment. We made many tests of the experiment to improve confidence in the results and never found any experimental reason for the low neutrino flux. Here are some of the tests we did. We did an experiment in which with a small tank of perchloroethylene, in which we introduced chlorine-36, labeled perchloroethylene. Chlorine-36 decays to argon-36, and we recovered the expected amount of argon-36, 100% with an error. In the big tank at Homestake, there's a reentrant tube. We introduced a neutron source, which makes argon-37 by an NP reaction on chlorine-37. Again, we recovered the amount of argon-37 that we expected. Another test, we introduced 500 atoms of argon-37 into the big tank and recovered them quantitatively. I was not told how much argon-37 was introduced until after I'd made the measurement and told how many should be there. We introduced argon as a carrier gas at the beginning of each run. We alternately used argon-36 and argon-38 so we could check recovery in each run by mass spectrometry after the argon-37 counting was complete. The counting efficiency of every counter used was measured. The solar neutrino problem lasted a long time. Over this period, neither the measured flux nor the predicted flux changed significantly. I never found anything wrong with my experiment. John Bahcall never found anything wrong with his standard solar model. In fact, with the advent of helioseismology, confirmed the temperature profile in his model. The discrepancy between theory and experiment was a robust factor of 3. Here is a summary of all of the data from the Homestake experiment. 108 runs were made after rise time counting was implemented. Over a period of 25 years, we detected 2,200 argon-37 atoms in the experiment. You can see that there's a gap here in 1985. This is about the time that I retired from Brookhaven and moved the experiment to the University of Pennsylvania, and also the pumps broke. So it took a little time to get funding to get new pumps. That's why there's a little bit of a gap in the data. My results from the Homestake experiment provoked a great deal of activity among theorists. Here are some of the more interesting alternatives to the standard solar model. The first suggestion here was a possibility that the luminosity doesn't match the current energy detection because light takes about 10 million years for the photons to reach the surface of the sun, while the neutrinos sampled the core 8 minutes ago. The second possibility, neutrino oscillations, was suggested first by Gribov and Pontecorvo. This is the same Bruno Pontecorvo who first suggested the chlorine-37 to detect neutrinos. Neutrino oscillations now seem to be the right answer. Some of the other possibilities now appear rather fanciful. Quark catalysis, helium-3 abundance being incorrect. Here are some more of these interesting ideas. Magnetic moment, that's still an unknown. neutrino decays, rapid rotation, burned out sun with a helium core, and accretion onto a black hole in the center of the sun. Some of these are quite amusing, but should be remembered at the time neutrino oscillations were viewed by most physicists as an elegant theory, but not very likely. The Homestake experiment was the only measurement of the solar neutrino flux for a long time. We had to wait for 23 years for another experiment, the Kamiokande experiment in Japan, to confirm that the solar boronate neutrino flux was low. The Kamiokande experiment will be discussed in the next talk by Professor Koshiba. In the 1990s, two radiochemical experiments that captured neutrinos using the inverse beta decay of gallium-71. And these measured lower energy neutrinos. The gallium experiments also show that there was a discrepancy between those predicted from the PP reaction, those expected from the standard solar model. So here you can see the chlorine experiment, the measurement and the prediction, the gallium measurement and prediction. I'm sorry, gallium here, and this is the Kamioka experiment here. The solar neutrino experiment seems to have now been solved with the first announcements of results from the Sudbury Neutrino Observatory, SNO. In 1985, Mikheyev and Smirnov proposed an elegant theory of neutrino oscillations. Their work built on the earlier work of Wolfenstein and the original suggestion by Pontecorvo and Gribov. Now known as the MSW effect, the possibility that neutrinos change flavor as they pass through matter has been an attractive solution to the solar neutrino problem for several years. The theory was given added support in 1998 when the Super Kamiokande team reported oscillations of high-energy atmospheric neutrinos from cosmic ray showers. In 2001, SNO released data in which they detected all flavors of neutrinos and found that their flux matched the standard solar model. All other previous experiments only detected electron neutrinos. Here is a comparison of all solar neutrino experiments for the standard solar model. Note that only the SNO experiments which detect all kinds of neutrinos actually match the predictions. When we started the Homestake solar neutrino experiment, we thought we understood how the sun worked and that a measurement of the solar neutrino flux would confirm the theory. This clearly did not turn out as planned. The collision between solar neutrino experiments and the standard solar model has ended in a spectacular way. Nothing was wrong with the experiments and nothing was wrong with the theory. There was something wrong with the neutrinos. Neutrino astrophysics is now a vibrant field with several solar neutrino experiments now collecting data and more on the way, not to mention high-energy physics experiments to investigate neutrino oscillations. I'd like to end by showing you what I found in my fortune cookie in a Chinese restaurant only 12 days before I heard about the Nobel Prize. I haven't yet figured out what the lucky numbers mean. Thank you.